Hello, folks. Once again, here we are. And boy, am I pissed. Because right now, well, we absolutely could be here. It's not that icy, not that rainy. It's not that cold. It's fine. It's fine. We're going to go over homework for Chapter 14 today. On Monday, I'm good. Before I start any new chapters, I'm going to give you chances to ask questions about all the homework so far. Some of you really need to work on some of that homework because, let's face it, this is Test 1 material. The NMR-IR crap, Chapter 13, Radical Reactions, and Chapter 14, Conjugated Reactions. If you haven't tried the homework, you're going to struggle on the test. Even if it's just like trying to figure out how they want you to input it. So, do work on that homework. I'll give you a chance to ask any questions come Monday. Now for lab, I plan on us to continue to try to start the spinach lab this coming week. After that, we will finish the spinach lab. It's a 2-week lab. And then we will skip the Diels-Alder lab. It's not that interesting, not that useful, considering we don't have a NMR. If we had an NMR, it might be still worthwhile, but without an NMR, not that interesting. So, with that in mind, we are going to just bypass that. That will keep us somewhat on schedule. Somewhat. But for now, I'm going to go through Chapter 14 homework. Let's look at this. So, insert the required reagents to perform the transformation shown. So, we are removing a double bond, and we are adding a bromine. So, specifically, we need to, we are adding a bromine in the one to the four in a anti-Markovnikov fashion for sure. But the first thing we can do for sure is adding, they might need to add another step, but we're going to add, let's see if we can do this. I think we're going to need to do reaction conditions. We're going to do 1 HBr, and then we're going to do let's see. Okay, let's see. How do I do this? HBr, and then H2. Let's see if that. Platinum. Let's see if that will work. But we want we want it in a slow fashion. So we're going to do it with heat. Let's see if that'll work. Or do I have to do that here? Okay. Let's see. Because my imagination is step 1. We add hydrogen first in a Markovnikov fashion, and we allow resonance to put the positive charge on the 4 carbon of that 1,3-butadiene. And so we would form a bromine right there and a hydrogen there, and we have a double bond there. The second step is just adding the second step is just removing the double bond. Okay, for God's sake. Let's see. See if that works. Comma platinum. We'll see. Yep. They are very forgiving. I didn't want it cold. Cold would have favored a 1-2 edition in a Markovnikov fashion. So I'm going to try another one. So we're adding CL right there. So I think we can just do HCl. Let's see if that'll work. Just HCl. I'm not sure if it adds like that. That might be only bromine again. Okay, HCl is good enough. Wow. Let's try one more. 1, 2. Okay, we want to add a bromine on both ends. So I'm going to try, well, what if we did a bromine Br2 instead of a H2? Br2 and comma, if I want 1,4 addition, I want it hot so I can get the 1,4 addition and not cold. Okay, so we're going to add another one. So the second step is removing the double bond. That's one of the double bonds. So platinum or palladium. We'll do palladium just to mix it up. Okay, so you're just looking at what are we changing. We're adding 2 bromines, and then we have to remove a double bond, because bromine normally just adds across a double bond. So very, very forgiving on that one. Which of these species are conjugated? It's not the best, but conjugation, not conjugated, because this guy's sp3 hybridized. sp2, 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 sp2. Not conjugated, because there's an sp3 right here and an sp3 right there. sp2, 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 conjugated, so, okay. Yep. If there is an oxygen in between, it can also be conjugated through that oxygen. sp2, 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 sp. Yes, 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 no, yes. Positive charge and negative charge. I'm going to do one more because this was easy. Yes, no, no, yes, yes. The carbonyl counts as a conjugation. So there's infinite different possibilities there. Write a second resonance structure. So let's draw this out first. The trick is, I always find, draw out your initial starting structure. If you don't have the starting structure right, you're never going to get it right. So, okay, we have a plus charge here, sp2, so sp2, sp2, sp2. So we got to rearrange this. We're going to move this positive charge and move that double bond. The double bond can only go to another sp2 carbon. So that means the positive charge has to move there. Now, which one is more stable? This guy is more stable. The structure on the left or the structure on the right? The structure on the right contributes more because we have a secondary carbocation instead of a primary carbocation. Draw two resonance structures. So, drawing this guy out again. Step one. Always step one. NH, put that with a plus, and where's that? O minus. O, 3 charges. Okay. Draw two resonance structures. Be sure to include all lone pairs. So I'm going to copy this over. So we're just moving double bonds around. Put a charge, put this lone pair, swing it down, delete this. That lone pair had to move somewhere, so there we go. Good. Bueno. Let's do that again. Okay. Now, I'm not going to include going the other way because delete, and you can do that as well. That also works. And I can also put a double bond, move the double bond back down there and put the negative charge there instead. But that's not really unique because it's pre-rotation. I mean, you can flip this around and make that other structure just by rotating the molecule 180 degrees. When the conjugated diene reacts with HBr, we form two products. So one 2 addition and one 4. Draw the curved arrow mechanism. So step 1, the double bond comes to attack there. I'm going to copy my structure over. God bless the copy function. Delete. Put a positive charge there and put, my bromine. We're going to just add boom, 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 boom. 4 lone pairs and 4 electrons. 4 lone pairs. And then we're going to just, where's this going to attack? Right there. Add step. We just gotta make a bond. Make a bond, make a bond, make a bond. We gotta delete the charge and put the bromine in. Now, do I need the lone pairs? I don't know. We're gonna put them in. But that is how we do the 1, 2. Now, here's where you're gonna get burned. Make the 1, 4. Make the 1, 4. Here's where you're going to get burned. This is why watching this video will help you from missing this the first time. So, same first step. Same exact first step. I'm just going to copy that over. Save myself some trouble. Boom. Charge, delete the double bond, put in a positive charge. Okay, all good. Now we're going to add a step. Okay. Here's where you're going to get burnt. So we're going to click, to do this, we're going to click Draw Edit, click this arrow, and we want to change this from a forward arrow, not to the equilibrium arrow, but to the resonance arrow. Even if you do the next step right, if you don't have the resonance arrow, you're going to get burned. Because what's going to happen is that's going to swing down to there. But this is through a resonance process. So I'm going to copy. We're going to delete, delete, positive charge, double bond. Now, you need that resonance arrow. It's not a single arrow because this is not a permanent move. It is a resonating between two positions. And it's all about when does this bromine come in? Where does the bromine bump into? If it bumps into one position, it forms the 1, 2. If it bumps into the second position, it forms the 1, 4. So I'm going to copy this guy right here. And just put the bond. Okay. So the trick is the resonance arrow. If you do not have the resonance arrow, you will miss it. Really smart people struggled on it. Why did I get it wrong? Why did I get it wrong? Even after they saw what the answer should be, they did not see the arrow. They did not know you could change the arrow. This arrow is what defines this from a one-way step to a so fast you cannot notice the change step. Okay, so how are we doing on time? Okay, still good. Determine the hybridization. Right there. So we have a sp2, sp2. This could be sp3, but it could be sp2. Why? If electron delocalization is possible, it will choose sp2. Let's see if I can. This guy is sp3 because electron delocalization is not possible. If there's no conjugation, it's lower energy to be sp3. If there is conjugation possible, sp2 is preferred. Conjugation with that double bond, so sp2. If it's possible, if there's a double bond nearby, it would prefer to be sp2. There's a lot of problems. Another one. Yes, definitely. Actually, your answer. Yeah, boom. Let's see if there's. Yes, sp2 because it's. Actually, no. sp3 because it's not possible. This is sp3 right here. You got to think about charges and what have you. Determine the relationship. Are they conformers, constitutional isomers, stereoisomers? So we have a cyclohexane, 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbons with substitution at the 1 and the 3 position. 1 carbon, actually, at the 1 and the 2 position. 1 carbon, 2 carbon, 3 carbon, 4 carbon. 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbons substituted at the 1 and the 2 position. So, hooray! They are not constitutional isomers. Now the question is, are they conformations or stereoisomers? So, this guy cannot have any different, but this guy would call that, in importance, this would be Z, essentially the cis isomer, and this would be a trans, well, like cis in respect for this, and this guy cannot have one. This guy would be trans. because we have this guy down and this guy up. Think about it. If I rotated this, so a rotation around this bond, the carbon 1, carbon 2 bond, this would be down, just like here. But this bond would be down. So these are stereoisomers. Stereoisomers. If I cannot rotate the bonds in order to make them fit, they are stereoisomers. Let's look at this guy. 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon. Substitute at the 1 and the 3 position. 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon. Substituted at the 1 and the 3 position. Okay. This guy is trans with respect to the double bonds. This guy is cis with respect to the double bonds. So we've essentially flipped here and here. So they're stereoisomers again. Let's see if I can get a constitutional isomer. Just trying again. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4. So it's not a constitutional. Okay. Now, looking at this. If I rotated this bond down, I get that. So this is a this is a conformation. This is an S trans conformer. This is an S cis conformer, but this relationship is a cis situation. This guy is a trans situation. It's still this guy is still a trans situation, so it's a conformation. We can rotate a bond to get this to look like that, to get A to look like B. The more conjugation, the more stable. That's pretty conjugated. I'm thinking it's going to be the most stable. 2 degrees of conjugation. No conjugation. Boom. Let's see if there's another one. We're looking for, I'm just looking. No sp3, sp3. So no, that's going to be least. There's 2, so it's probably going to be 2. 1, 2, most. The more conjugation, the more sp2 lined up in a row, the more stable it's going to be. 3 major products. So if I add HCl, I could add here and add a chlorine there. Is that a shown product? Okay, yes. 3 major products. Disregards, check all their play. If I add here, this double bond flips here. I could add a chlorine there. Is that one shown? Oh yeah, here we go. And if I add here, hypothetically, I could add there or there. 3 major products. I'm trying to think why. There should be 4 major products. I wonder why one does not form. Oh, one of these being major. No, that one's definitely not. I don't think the book talked about this very well, so I think I'm going to go with that. I don't know. I'm gonna try removing this one. Okay. See the explanation. The book didn't really talk about HCl very much. One ABC and ABC all come from 1-2 addition. ABC. However, major 1-2 addition is structure A because it's the most substituted double bond. Okay. It's more reactive to electrophilic addition. B, D, and E are 1-4 and have similar reactivity, so both will form. Okay. So 1-4 is preferential, but because 1-2 has one of these guys having a more substituted double bond, it makes that one slightly more reactive. Okay. It's just a nature of HCl. Product, so we can have 1-2. Product B, the 1-2 product. So product B is the 1-4. So we added here and here. The thermodynamic product is always the 1-4. Okay. Consider the following compound. Draw the structure of the diene that could be used to form this guy. Oh, crikey. So we gotta work backwards. So I'm gonna put. Of course they did this crazy ass structure. Okay. O wedge. These are just bells and whistles, folks. Okay. A diene. So we have a add a chlorine right here. So one. So this is a diene. Diene used to. Oh, okay. I think we have a Diels-Alder here. Okay. Select the diene. So I'm gonna. Oh, damn it. Fool. So there's a Diels-Alder. We're now into Diels-Alder. So we're looking for a 6-membered ring. The diene has the double bond between it. I was tripped up by the chloride. So, with that in mind, the double bond between that becomes the diene. And unfortunately, I don't get to keep this. I'm upset. Oh well. So, la vie. So, I'm going to see if I can copy that. Oh, no, can't. Gonna trash it. Okay. So there's my diene. Oh, I have to. Fuck. Okay. So. The dienophile is the group that reacts. Now, because they're both wedged, this means they're both cis. They had to add in a cis fashion. If one was wedged and one was dashed, then it would have to be a trans dienophile. But so I'm just taking my 6-membered ring. Where's the double bond? The double bond is between the 2 and the diene. So we're working backwards. Okay. So we have a trans diene and a cyanide. Draw the product. So rotate this into a cis. Can we rotate it? Yes. This is what that would look like. There's my cyanide. Just put CN. So, I'm going to make that. I'm going to draw my bonds in and then break my bonds. I know that's bad. So, break that, break that, break that. Now I have to make that a wedge or dash. It don't matter. This is omit stereochemistry, so it doesn't matter because whether that's wedge or dash, you're going to get both. Draw the diene and the dienophile. You need that. So once again, we have that 6-membered ring. In this case, the 6-membered ring is attached to a 6-membered ring or two. Okay. So we're going to do 6-membered ring, 6-membered ring, 6-membered ring. Beautiful. There's my diene. That's fine. It's ugly, but it's fine. What's the dienophile? This whole molecule. This is what I mean. Why is this a freaking useful reaction? It's like, oh, you've made a really, really complicated molecule out of... I mean, don't get me wrong, it's a complicated molecule, but relatively simple molecules. That's a pretty complicated looking thing after a substituted, the cyclohexene. Place these in order of reacting to Diels order. Okay. I can rotate this into a cis. Is it the best cis? No, but it can be. B is the lowest. B is the lowest because it's stuck in the S trans. C is going to react the highest because it's stuck in the S cis. So we're going to have B, then A, and then C. Anytime they're stuck and they cannot rotate, it's going to increase or decrease the reactivity. So A is going to be the most reactive. It's stuck in the S cis. B is the least reactive. And C, of course, is the middle guy. Because can rotate, can't rotate, can't rotate. We want them in this cis fashion. Got 3 more. 3 more. We're working our way through. Taking our sweet time. Okay. 2 molecules of the compound react in a Diels-Alder cycloaddition, where one molecule acts as the diene, the other is the dienophile. So remember, you should have a 6-membered ring and another 6-membered ring. So we have 1, 2, 3, 4, 5, 6. There's a 6-membered ring. 1, 2, 3, 4, 5, 6. 6-membered ring. However, we should have a total of, since we start with 2 alkenes on each side, we should have 2 alkenes in the product. So A is wrong. B is possible. No. Because it should be a 6-membered ring and a 6-membered ring and only 1 alkene. So rank the following dienophiles in order of the more electron withdrawing groups, the faster they react. C, B, A. Try another one. Is it really going to be that easy? The better the withdrawing groups, the faster they react. So A, B, let's see, C. Even though CF3 is pretty dang electron withdrawing, 4 cyanides greatly outweigh. And finally, draw the product, including the stereochemistry. More than one product forms, draw only one. So, we have our... once again, I'm going to draw my diene in the proper conformation. Draw my dienophile in the proper way. It will help me for later. Okay. And I'm going to delete bonds as I see fit. Okay, there we go. Perfect. So I am going to make a bond here. Those guys go away. Make a bond here. This goes away, and the double bond forms there. There's my dienophile. What? Oh, includes stereochemistry. Oh. So what that means is I got to click that and let's see. Perfect. Now let's see. Wrong. Got to redraw that arrow. It can be wedge up. It can wedge down. But you're going to have this folded up and folded down. There we go. That is all of Chapter 14's homework. Obviously, you're going to have your own problems, but hopefully that gives you enough guidance that you can manage to try these on your own. I'll see you on Monday.